Hi everyone, this is Jim Pollock, and you're watching my lesson video for SSCI 599 about constructing models in the NOVA modeling package. There's a lot to discuss, so let's move to the next slide and begin. Okay, so we'll begin with the lesson objectives. And when we finish the lesson, you should be able to state the components that make up the NOVA environment and also be able to describe and articulate many of the components that go into NOVA models themselves. You should also understand the general workflow that goes into creating NOVA models, which, as we'll see, begins long before you ever touch the software. It's entirely achievable by viewing this lesson to create a simple NOVA model, because NOVA is very intuitive. But it's also very broad and has many implementation options. And we'll go over a lot of those options and show how a lot of these options are being used in the academic and research environment today. So at this point, you're probably wondering, what the heck is this NOVA? Well, I can tell you it's a brand new, released in 2013, multi-purpose modeling package that closely resembles the commercial Stella modeling package. In fact, it resembles Stella so closely that I was wondering myself how the Nova creators stayed out of court. So it's a graphical interface that uses systems theory to construct a variety of models. But what distinguishes Nova from Stella is its spatial capability, and how it accomplishes that we'll see as we go along. So similar to what we did with our NetLogo uh, assignments, you can use Nova to model things like changes in a landscape, cellular automata. You can do agent-based models or combinations of the two, which Nova calls sim worlds. And if you're familiar, you can even do neural networks, which is far beyond what we will talk about here in this lesson. What you can't do is model things like fixed networks or static models like a DEM. And for now, we can't import real data, but there's GIS integration coming soon, and so look out for that. So let's take a look at NOVA itself. Okay, so this is the NOVA environment, and with a very simple population growth model loaded, and we'll use this to take a quick tour of NOVA. We'll start with this window, which is the programming window, where we can enter JavaScript code that would affect the model globally. And incidentally, if you're very good at JavaScript, you're going to love Nova, because just with some simple JavaScript code, you can make very sophisticated models. This is the console window where we can check for errors and test and debug code. This is the capsule window, which lists our parent model in bold, and then this one doesn't have any, and any submodels we might have. This is a distinguishing bit of Nova. This middle pane is the model canvas, where we can simply drag and drop components to a model like this and connect them and move them around. This is the dashboard that contains user inputs such as this slider, or outputs like this graph or this table. Above we have the clock settings, and then a toolbar which can run our model or drag and drop components, etc. To run the model, we would simply hit capture, which takes all of this graphic components and turns them into JavaScript. Load, which loads all of our variables, and then execute, which executes the model. It's quite simple. Components in that are very common would be a stock, which is simply a container of values, and those values are updated by a flow, which is essentially is a something that, and we can click on this and see it's pop times rate, which is essentially a representation of a differential equation or change over time. And rate, pop is the stock, and the rate comes from this term, which if we open up is birth rate, which comes from this slider. Very simple. And then as the model runs, the population updates the graph in the table. And that's the basics of how a NOVA model is put together in the modeling interface. Okay, so now we'll talk about a few key NOVA terms and concepts that make spatial modeling within NOVA possible and weren't presented in our brief overview. First, we have the agent container, which is a component that contains the spatial bits of the model. It could be a cell matrix, which a grid or a hexagonal grid, or an agent vector, which holds logic for agent movement, or maybe a sim world, which combines the two. And the logic for these agent containers are contained in a capsule, which is a model within the main model. And that's what makes NOVA unique. Next, we have a code chip. And a code chip is a drag and drop component that can contain snippets of JavaScript code that can take multiple inputs, multiple outputs, and replace the simple parameters that we can make into, say, a flow or even a stock or a term. And then a cell matrix is an agent container that is specifically geared towards a cellular automata, and we'll use one of those in our example model. A pin is a component that, if you imagine an electronic circuit board that communicates between the black box of the submodel capsule and the parent model, it moves information back and forth. And then the raster plugin is a component that appears on the dashboard and shows the cell matrix as a raster object for visualization. So with a basic understanding of the NOVA environment and some of the components that make up NOVA models, we can move on to modeling a spatial model in the NOVA environment. And the basic process is depicted in this diagram. There are three basic components, and first we need to have an analysis goal. Obviously, no modeling environment is useful without something to model. And then we need to conceptualize this goal that we have. How we think about how do we spatially depict it? How do the bits and parts work together? And then, if we get an output, how do we validate it? Can we break it, or is it consistent? And then finally, we need to build a model, and then run it and analyze it. There is an expanded version of this diagram in your handout, and it might behoove you to have that handy as we talk about the modeling process, so you can see where we are as we move through the various steps. To demonstrate NOVA, we thought it would be interesting to model a controversial forest dynamics theory by ecologists Herbert Borman and Gene Likens. And it's known as the shifting mosaic steady state theory. And this theory states that in a forest ecosystem is defined by patches of different species compositions that are undergoing varying stages of succession, which is the replacement of one species set to another. For instance, one might be bare ground, which moves to grass brush, which moves to sparse sun-loving trees and on to a mature thick forest, and then a disturbance such as a fire might move that back to barren ground, and so on. Those patches will continuously change due to that process, but the overall ratio of the species within a defined area will remain static. So our analysis goal is to see if the pattern of shifting mosaics steady state will hold using the author's rules, and we'll see if we could break this pattern of ratios using simulated management actions. With the topic in hand, we need to conceptualize the model that will represent it. And that's accomplished through a series of steps. And the first is to simply think about the system. And this sounds trite, but it's pretty darn important. Bowman and Lycan clearly state that they view the forest as a matrix of patches, so cell matrix is an obvious choice, but there are things to consider. A hexagonal grid, how should we manage the clock? And you might consider this the data search for this sort of model, but instead of representative data, we're searching for representative logic. And we're lucky that we have the O'Sullivan text because it catalogs this sort of logic. Ordinarily, you might have to sift through the literature, but as it turns out, the rock, paper, scissors interacting particle system in the O'Sullivan text nearly duplicates the rules set by Borman and Lycan. So if we have a conceptual working model, that's great, but we need to validate it. Can we break it? Is it going to be consistent over many iterations? So we need to find a way to insert things into the model where we're able to test these things. And we decided that we would test the hypothesis by varying the probability that a disturbance will occur or that succession will occur. Okay, so we're back in Nova with our concept in hand. We're going to implement it in Nova. And so, just for the record, all of these components you see are described in intimate detail in your handout, so we'll go over it in a general way here. But always the first step, you want to start at the lowest level. And the model that you see here is the logic for updating the state of each cell in our matrix. And this particular stock, called plot state, represents the value that will be updated to each cell in the matrix at each time tick. This flow tells the stock how to update itself on each clock tick so that it will change over time. Now, instead of just inserting some simple equation inside of the flows we've seen before, we used a code chip because we have multiple inputs that go into the flow and also information about the current state coming out of the code chip. So if we open this up, we can see this is the code that was written, and this code is in your handout. And it's basically a random number, and then it says, hey, what is the current state? And if the odds say, we'll switch it to the next available state. So we go from 0 to 1 to 2 to 1, 3 to 1, that sort of thing. These pins are what define the probability within the code chip, which of course supplies logic to the flow. And these pins are connected to the upper level where user input sliders are. And then, of course, this pin takes the logic from this model and sends it to the upper level. Next, we'll look at the parent model that this code relates to, and we'll do that by clicking here in the capsule window, and here it is. And you notice this is the cell matrix component that this logic is embedded in. These pins that you see relate to the pins you see in the submodel. So if we open this, you can even see that this cell submodel is embedded within this uh, chip, and that is the bit that makes the spatial modeling possible. Connected to these pins are these user adjustable sliders that change probability. And then we have a viewer, which we'll see in a moment, that visualizes the matrix that's in here, a 55-15 matrix. This code is to produce an output of readouts of the ratio so we can see how those change over time, and then a chart that displays the change in ratio over time. Okay, it's time to run our model, so I'll display our dashboard, and I've preset all of our probability sliders to point to with the exception of disturbance. And that's the only one I'm going to play with, just to demonstrate perhaps how we prevent fire or allow fire to occur. And then up here I can make some initial conditions. I can flip things around. I can just leave it as barren ground. I can add some brush or perhaps mid or dense forest. So we'll capture load exec, and with this speed relatively slow, we can see as the ratios are moving along. If I say I'm going to prevent all fires, we end up with almost complete dense forest. Now if I move back towards um, allowing most fires to occur, we set up back with, I'm going to speed this up, we set up with a stable but different ratio of species composition. So what this tells us after a single iteration is that we can break the pattern, and management of, actions can change forest composition. Obviously, we need several more iterations to validate this, but it is interesting. Quickly, I'll mention that Nova is very new, so Nova projects haven't had time to filter into the literature, but there are ongoing projects. For instance, this gentleman is studying epidemics in Africa, and this is his model. And it's got several layers where we have incidents of uh, a disease, the individuals, communities, and an entire clinical study area. And NOVA is also being used in education to teach prestigious universities such as Stanford and Berkeley to teach modeling, because it has several different modeling methods that can be broken down into simple graphical components and code snippets. Finally, a few tips and tricks. First, Nova has an extensive model library of sample models, and it may be intimidating to build your own first real model, but you can cut and paste from those sample models and patch together a great model. It's an excellent and completely legitimate method. If you're a programmer, the NovaScript library has tons of methods that can take 10 lines of codes and to squish it down to one or two. And finally, watch the tutorials. They're great, they're video, and they're updated all the time to help you learn about Nova. So give Nova a try. It's a great system, and I'll talk to you soon.